Okay, this week I just wanted to go over a little bit about the tools and the process for performing a hydrometer analysis. And this is also now the third of our grain size analysis labs where we went from the coarsest procedure of the wet sieve where we separated things out along one um, grain size. Last week we performed the dry sieve or the mechanical sieve where we were able to develop more of a gradation, right, along different particle sizes to reflect the characteristics of our soil based on uniformity and I guess grain size distribution, and then we retained the smaller pieces out of that sample to perform now this week the hydrometer test. And the hydrometer analysis is exclusively done on small soil particles. So look back at that picture we saw last week where we had an original soil sample that's broken out here into components along those various sieve sizes. And the idea here is if you combine these smaller particles into a kind of a homogeneous sample and then add them to a solution of water, the larger particles are going to settle out first, the next largest ones will settle out, and ultimately, if you wait long enough, the finest particles will settle out. And as those particles settle out of your suspension, the density of your solution changes, and that change in density allows us to calculate the properties of these soil particles. So this, I guess, the theory behind this is about Stokes' law, which states particles in suspension will settle out at a rate that varies with their size. And in plain English terms, a larger particle is going to settle out first. Smaller particles are going to settle out last. And when you have a particle, a round spherical particle in a liquid solution, you have two forces acting on that particle, right? You have gravity wanting to pull that particle down, but then because you have that real dense environment, you also have drag forces, which are kind of resisting gravity. And they're not pushing up, but they're counteracting the force of gravity. And that particle is going to accelerate down through your solution or your fluid until it reaches equilibrium, where your gravity force is equal to your drag force. And when that occurs, we call that terminal velocity. And your particle no longer accelerates, right? But it maintains a consistent velocity, terminal velocity. So the device we use is it's kind of like a glass bobber. It's called a hydrometer. And a hydrometer measures the density of the water-soil suspension at periodic time intervals as the grains settle out. And you can see the top of that bobber. This is the readable part of the scale sticking up out of the top of the solution there. What we're measuring with the hydrometer ultimately, or what we're calculating, is the size of the particle that is settled to the center of the hydrometer. So this hydrometer kind of has a center of balance, right, the middle of that bulb, and as the density of this solution changes, right, it's changing because these larger particles are settling out, so the solution is becoming less dense. It's returning to plain water over time. What we're actually doing is measuring the density of the fluid at the center of these hydrometers. So over time, the hydrometer is going to fall lower and lower. And the density of the solution simply indicates the percentage of the sample still in suspension. Right here at the beginning of our test, most of the particles are in suspension. Our fluid is at its highest density. And at the end of the test, we're at the lowest density or the least density. So there's a key distinction here that we're going to have to be aware of when we perform this test. the type of hydrometer being used. There are two types. Both of these are ASTM um, uh, uh, ASTM standards. We have a type 151 hydrometer and a type 152 hydrometer. And the obvious or the most apparent difference is how the scale is graduated out. And you can see here on the 151 hydrometer, this would be your initial point, or your essentially 0 point, and it reads 1.000. Whereas over here on the 152 hydrometer, your 0 point right here reads 0. The 151 hydrometer goes from 1.000 up to about 1.030. Your 152 hydrometer simply increments up in integers: 0, 10, 20, 30, 40, 50, and so on. Right? And the difference here is that the 151 hydrometer is graduated to read the specific gravity, which, if you remember from our week 2 discussion, specific gravity is the same as relative density. It's graduated to measure the relative density of the water-soil solution. Right? So think for a second here, what's the density of water? Right? We know that's the number we've been using now almost every week. The density of water is 1 gram per cubic centimeter. So when you stick this hydrometer in plain water, it's going to read right there. That's its initial baseline, or the control line, 1.000. It represents it's in a body of solution, not even solution, it's in a fluid with a density of 1 gram per cubic centimeter. The 152 hydrometer is graduated to read the density of solids in suspension in units of grams per liter. So it's not measuring relative density anymore. It's measuring actual density. And actual density in plain water is 0 because there's no soil particles in that solution, right? So as we add soil particles, the density of our water, right, in grams per cubic liter is going to change, and this will float higher, and we'll actually be reading a value down here along the graduated portion. The calculations used to to calculate percent passing are different for each hydrometer, so you need to be aware of the hydrometer that you've been using throughout the lab this week, and also don't mix up hydrometers, so it could cause some calculation problems. Percent passing in the hydrometer test is directly analogous to what it meant in the dry sieve test, where percent passing meant what percentage of our soil sample that we're using in this test is smaller than the diameter we're now calculating. Right? We were able to directly measure that with the dry sieves because we're using pans with screen sizes that had openings in them. And if we measured the mass of particles that went through a pan, we could calculate the percent passing. So essentially what this represents is a grain size calculation. So this is kind of the test equipment that we'll be using this week. The most fun piece of equipment here is the milkshake mixer. We use a tall beaker, a 1 liter beaker, to perform the hydrometer in. We have to mix up our soil sample and let it soak in a solution. And we have a hydrometer to use. And the steps to perform the hydrometer test, they're really fast and furious at the beginning. It's going to be kind of, I'll try not to make it hectic, but it's going to be busy for the first 15 minutes, and then things really slow down, and you just have to wait between your time intervals. But the first thing to do is to retain the fines of a soil sample and then soak them in a solution of 40 grams per liter of sodium hexametaphosphate. And that's what we've done. We've retained our small fines from last week's lab, and they've been soaking this past week. We then add that those soil particles, we wash them out so we get everything out of the bowl, and we put them into a milkshake cup. And we break up the potential clay clods, right, the soil clods, in a milkshake mixer for 60 seconds. And then we'd have to take that milkshake cup and wash out all of the fines into our 1 liter beaker, um, making sure that we get all the soil particles out of um, our containers and into that beaker, and then we bring the level of our water up to that 1 liter kind of control line. We're going to put a rubber stopper on top of that beaker, and we're going to rock the beaker back and forth for 60 seconds to equally distribute all of the soil particles throughout this solution. And then we set the beaker down and immediately begin a timer and insert the hydrometer into the water, or into the solution, and record the height reading along the scale at time intervals. Those time intervals are generally pretty quick at the beginning, maybe every 1 minute, and then 5 minute, and then 15-minute intervals, and then they start to space out, say 30 minute, 60 minute, 120 minute. We'll go as long as time allows us in our allowable lab time. A true hydrometer test measures this over 12 hours. It could take that long to really get your fine clay particles to settle out and change the density of that solution. So if you remember last week, we talked about the gradation curve, and these coarse sieve screen sizes were able to be determined through a mechanical sieve action, but it was this last portion here, right, the portion smaller than our number 200 sieve that's identified as hydrometer analysis, that needs to be done, or needs to be accurately filled in using the results from this week's lab. And one last little point of to bring out, this picture makes me laugh because this was a student 7 or 8 years ago now, and Montana Tech hired some professional photographers to come in and take marketing photographs to highlight some of the classrooms and the lab work and the students, just general pictures. So the photographer had Fred here take a hydrometer flask and put a hydrometer in the water, and if anybody knows what they're looking at in this picture, they know the student here is doing absolutely nothing of relevance, because you wouldn't actually read hydrometer readings in plain water. They made for a nice picture, but if someone actually knows what they're looking at, there's a meaningless test going on here. So it still makes me laugh when I see that, and I'm glad it's not used anymore in circulation.